Before we continue, let's prove Green's theorem, which is going to be useful to derive another result from the Poincare invariance. Green's theorem is a direct consequence of the Stokes theorem, which you remember from your basic calculus. If you have a function f around a path, say c, Stokes' theorem states that the line integral of the function f along the path c is equal to the area integral of the curl of the function, where dA is along the normal to the area. The rationale for this is also the reason why the Stokes theorem is called the circulation theorem, and is that if you divided the area into micro circulation, all of the internal circulations are going to cancel out, and the only thing that remains is the circulation of the function f along the boundary. So say that you have this function f divided into a function little f of xy in the x direction, plus a function g of xy, which is in the y direction, and the curl then is pointing in the z direction. So Stokes' theorem then becomes the surface integral of the g dx minus df dy, where dx dy is equal then to the line integral of f dx plus g dy. Now for the particular case that we have f, the function f being minus y, and g being equal to x, this becomes the line integral of x dy minus y dx is equal to twice the area. You can see that the closed integral of y dx is equal to minus the closed integral of x dy over the same path. This is seen because imagine that you have, let's say, a simple surface. This is x, and this is y. The integral of y dx means that you have a height y and a small width dx. Now, if you sum all of the small contributions, then you have the integral over the curve. And the path of integration is as dx is increasing, so is in that way. The path, therefore, is counterclockwise. Now, you can think of the same curve and integrate now not in x, but in y. So now your curve is going to be x with a small width dy. But now dy is increasing upwards, so you are doing this integral clockwise. So indeed, the integrals, in the end, they have the same modulus, but because the orientation that you're taking the integral changes, one is the negative of the other. So proving this, we go back to the equation that we had. And if the integral of y dx is equal to minus the integral of x dy, then what you have is that twice the integral of x dy is equal to twice the area integral. Therefore, the closed path integral of x dy is equal to the area integral of dx dy. And this is Green's theorem. As I said, it's a direct consequence of Stokes' theorem.